All right, everyone. So here we have special theory of relativity. Up to this point, we have been looking at classical physics. That means all the concept, including Newtonian mechanics, basically that gave us laws of motion, waves, thermodynamics, um, electricity and magnetism. Those are all considered to be a classical physics, and everything more or less was developed by end of the 19th century. That means you can go back to the Galileo's time, so basically 17, 18, and 19th centuries. That's where all of those concepts basically developed. At the end of 19th century, um, Maxwell gave us laws of electrodynamics. That means we have this Maxwell's equations. And one of the important things that came out of that was that light is an electromagnetic wave. Now, light being electromagnetic wave means that we now know what the light is, and we know how fast it's moving. And when we start, let's say the scientists, when they started doing experiments and they started doing, theoretical investigation of light as an electromagnetic wave, they realized that classical physics breaks down, especially when you look at when objects moving very fast, where the speed is comparable to the speed of light in vacuum, or when we look at objects that are very small, like subatomic particles, electrons and protons and things like that. Classical physics breaks down. It cannot predict the outcomes. That's what I mean by breakdown. That means the result and the predictions don't match. Well, that's why in 20th century we have sort of like a revolution in physics where some of those classical ideas had to be left behind, and we had to then develop some new ideas, new branches of physics to try to explain things that now we are um, experimenting. So the results of the light um, can only be explained now with the special theory of relativity or quantum physics. That means when we talk about the physics of very fast, then we have to look at special theory of relativity. When we have to look at physics of very small, then we have to look at quantum physics. And obviously, one of the things about this modern physics, right, the relativity and quantum physics, is that they're bizarre. They're very weird, and there's some incredibly, counterintuitive, consequences. So, for example, here we're going to study the, special theory of relativity in this chapter, and we're going to see some of the, really incredible effects of the objects moving fast. Here, let's say we start with this image over here. This is from a science fiction book that was written in 1940. It's called Mr. Tompkins in Wonderland, and it was written by a physicist, George Gamow. Now, what we do in this image is, or in this book, right, is we assume that speed of light is only 10 meters per second. So here, Mr. Tompkins basically reads a book on relativity where he realizes that when you are moving relative to other objects, right, when basically you're moving fast, then things change, right? So basically, one of the things we're going to see here is there are some consequences of object moving fast, closer to the speed of light. So let's say right now, in this book, we assume that the speed of light is 10 meters per second. So if you move at 10 meters per second, which is roughly 20 miles an hour, then we can feel that relativistic effects. So, and Mr. Tompkins has been worried about the change in his figure, so he was happy that if he starts moving fast, then he can see himself getting thin. While when he started riding his bicycle close to the speed of light, or let's say 10 meters per second. By the way, nothing can move as fast as speed of light, but you can get very close. So, but let's say he's moving at comparable to the speed of light speed. And remember, in this book, it's about 10 meters per second or 20 miles an hour, hoping that he will change. He will see, changes in himself. But what he realized is, exactly the opposite. There's absolutely nothing changed about him. So he was just like before. He started moving at 10 meter per second. What he noticed though is that everything around him changes. Okay, everything around him changed. So you have the streets getting shorter, the windows becoming very thin, like a thin slits, and the policeman basically becoming very thin man. So he then realized that what we mean by theory of relativity is that things change relative to you if you're moving very fast. By the very fast, we mean in a way that's speed compatible to the speed of light. That means what you see here is you see your environment changing. Or if you're an observer, right? That means, for the observer observes, like, let's say, changes in the environment. All right, so those are the things we're going to be studying in this chapter. That means when objects moving very fast, we will see changes in length of the environment, or some kind of measurement, or changes in the time of measurement. But it all has to be relative. you know doesn't matter how fast you're moving, your clock will not be any different than if you're just sitting in your room and not moving. Okay. The idea here is that it will be a change when you compare yours, let's say your clock, relative to something else that moving differently, or different speed, different direction relative to you. All right. So that's sort of like, let's say, the concept that we're going to be studying in this chapter. Okay. Now let's go back, look at the Newtonian mechanics. We can see, right, the Newtonian mechanics fails to describe properly the motion of object whose speeds approach that of light. That means for everyday applications, Newtonian mechanics works perfectly fine. You want to build bridges, cars, airplanes, space shuttles, and things like that, right? Perfectly fine. Newtonian mechanics can give you exactly correct calculation, and you don't have to worry about anything else. But if you try to look at, we're not there, but let's say when we get into the um, let's say time where we can build spaceship that can travel from one solar system to another solar system, Newtonian mechanics can actually break down, because then we have to move really fast. We have to build something that can move fast enough. And then this concept requires special theory of relativity, or general relativity. And that's what we're going to see here. Some of the calculations, some of the equations that we had used before have to be modified. So, like, let's say the relativistic effect has to be applied to them. So that means Newtonian mechanics, you can see that, is a limited theory. It places no upper limit on speed. That means according to Newtonian mechanics, you know, you can move faster than speed of light in vacuum. Well, and that obviously have not been absorbed. So experiments um, don't agree with this theory. The experiments show that there is a limit to the speed, and the speed is 3 times 10 to the 8 meter per second, and the only thing can move at that speed is the speed of light. Basically, is the light. Only light can move at that speed. Only in vacuum. You know, light actually, remember, slows down when it goes into more dense mediums, but in vacuum it moves at the speed of light. See, but that's the fastest it can move. Nothing else can move at that speed, and nothing else can move faster than that. Okay, so that's already a contradiction there. Um, so then what we're going to do here is Albert Einstein basically came up with this special theory of relativity. So one of the things we're going to see, this term relative, right, the relativity, is not really unique to Albert Einstein. So this is not necessarily, at least, this term relative. We have used it even before when we talk about relative velocity, relative motion, right? So one thing we'll see that there's a classical relativity theory, right? So of the theory of relative motion, and then we're going to see that there is a more modern one where we do have to apply this relativistic effect. Okay, so that means one thing we can see here is when you then talk about the more complete theory, is Einstein theory is more complete because it takes into account slower speeds and faster speeds. That means you can say that Newtonian mechanics is a special case of the Einstein's theory of relativity, special theory of relativity, because Newtonian mechanics is part of the Einstein special theory of relativity when objects moving slow, but then it cannot describe a fast moving object. Special theory of relativity can do both. So that's why it's a special case of that Einstein special theory of relativity. Einstein gave us two relativity theories. One is a special theory that deals with speed, object moving very fast, like a speed, compatible to the speed of light. He also gave us general relativity, which is completely different concept. It's a concept that actually replaces gravity theory. So I highly recommend you guys check it out in terms of what is general theory of relativity, and that's basically another way of describing gravity. Okay, so which is incredibly insightful, like really probably one of the most brilliant ideas in the entire human existence. So that concept of general relativity, right down that Einstein came up with to describe gravity. All right, so here's then what we have. To describe a physical event, a frame of reference must be established. That means one of the things we're going to do here, we're going to then sort of like, let's say, develop or look at classical theory of relativity and show that how it can break down when we apply fast moving objects. And then we then modify that with, let's say, relativistic factors to then be able to describe, let's say, any type of object that is moving fast. All right, so one thing we have here is to start with developing those theories, we're going to talk about um, frame of reference, because whenever you're doing some kind of experiment, you want to have, and this is also something that we always do in the beginning of studying physics. So every time we start concept of force, so if you can go back and review it yourself. So when we talk about Newtonian laws of motion, we always talk about reference frame, and we always talk about inertial reference frame. So there are two types of reference frames. Reference frame where laws of Newtonian physics were obeyed, we call that inertial reference frame. That means that's when we studied Newtonian mechanics. Studying Newtonian mechanics, we always established some kind of reference frame, and we said that if you have a reference frame that obeys Newtonian laws, then that reference frame is an inertial reference frame. There you go. Which is, for example, right? So that means you do an experiment over there, and it agrees with the prediction. Okay, for example, you have a very simple experiment. So you're standing here, you put let's say, a ball, soccer ball next to you, and if nobody's kicking the soccer ball, it will just stay there, because Newton's first law tells you that object is at rest, will remain at rest until some external force acts on it. Okay, but if no force acting on it, nobody's pushing or pulling or kicking, it will just stay there at rest. Okay. Now, one thing we have here is the same experiment can be done if, let's say, you're in a bus. Let's say you're in a bus. So you can put that ball next to you in a bus if the bus moving at constant velocity. That means if the bus moving at constant velocity, you can still do that, right? So that's why, for example, the airplane, right? When airplane is on autopilot, basically moving at constant velocity, you can just put a hot cup of coffee in front of you and then just enjoy the coffee, and without not worrying about, let's say, spilling it on yourself and things like that. That means you can treat this as just like you're sitting in your room, but only when the airplane is moving at constant velocity, right? So one thing we can then say is that in order for the frame, the reference frame, um, to be inertial reference frame, that means it has to obey the laws of mechanics. Okay, that's what we want. So the inertial frame is one which an object is measured to have no acceleration if no force acts on it. Any frame moving with constant velocity with respect to an inertial frame would also be an inertial frame. That means I can take this to be inertial frame. So let's say you're outside just sitting there. I can say that, okay, so that's we're standing there with the ball next to you. That's an inertial reference frame. But then someone else moving, in a moving bus, repeats the same experiment and gets the same result, then we can say it's an inertial reference frame as well. Well, in order for it to be inertial reference frame, it has to be moving at constant velocity relative to u. So the inertial reference frame is the reference frame that is not accelerating. Any accelerating reference frame is not an inertial reference frame. So the laws predicting the results of an experiment performed in a vehicle moving with the uniform velocity will be identical for the driver of the vehicle and the hitchhiker on the side of the road. That means as long as two observers have velocity, even if there's different velocity, but they're moving at constant velocity relative to one another, they then can say that Newton's laws of motion will be obeyed, so their measurements will agree, like we're going to see in the next few slides. So let's look at what we call the principle of Galilean relativity. As you can see, right, this principle is pretty much is the time of Galileo, Isaac Newton, and it has been around for a long time, so this concept of relativity. So the principle of relativity states that the laws of mechanics must be the same in all inertial frames of reference. Right? That means laws of mechanics is the same, and that's the key, right? So we're going to see that later on. This laws of mechanics means that Isaac Newton's laws of motion will be the same in all inertial reference frames. So here's a couple of ways we can look at it. So you have an observer in the moving track. Okay. If you're an observer in a moving track, for example, this guy over here, what he will do, let's say he throws the ball up. So the ball gonna be moving straight up, will go reach some height and come back down. Again, we're assuming that the track is moving at constant velocity. Okay. If the track is moving at constant velocity, if you do this experiment, what you will see here is no different than if you would have done that in your, let's say, physics lab. So if you throw the object up, it will go straight up and straight down. Okay. So this is just pretty much, a one-dimensional free fall, right? So we studied this in the chapter 2. So it's just one-dimensional free fall. If you have a observer that's going to be looking at the same experiment that is done by the guy in a moving track, for example, here, she will see something different. The stationary observer then will see that path is not straight up or down, but it's a parabola. Okay, it's a parabola. So she will see this as a projectile, which is a two-dimensional free fall. Okay. But one of the things we did when we studied one-dimensional free fall and a two-dimensional free fall was that if you're looking at the time of the object going up and down, straight up or straight down or projectile, it's going to be exactly the same. So the only difference here is here the object has only vertical velocity. Remember, so the vertical velocity is equal to 0 at the top, and then it goes straight down. Here, if you look at just the vertical component of that, you can see that it has a vertical velocity. Here, then vertical velocity is 0. Then here, then vertical velocity will be something like that. V final, right? So for the vertical velocity final, which means that final velocity in a vertical direction and initial velocity and maximum height velocity will be exactly the same for both experiments. Okay, so here when it comes back down, we can measure to be exactly same final velocity. The only difference here is that the ball has a horizontal velocity component, Vx, which actually will be matching the track velocity. Okay, because when you do this experiment in the track is moving, then the ball will always have the same horizontal velocity as the track. This is exactly the only difference between the experiment absorbed by the person in the truck and by the stationary observer. So one thing they will do then, they will both agree the motion obeys the laws of gravity and the Newton laws of motion. And both will agree how long the ball was in the air. That means if you measure the time going straight up or down or the projectile motion, the time is exactly the same. So if both of them agree on measurements of the time and let's say vertical position, right, which let's say the motion of the ball, then you can say that uh, those reference frames were inertial reference frames, and the Newtonian mechanics laws were obeyed. Okay. Even though the let's say the truck was moving at a different speed relative to the observer, stationary observer. All right, so now that's basically the example of how we start in terms of like let's say looking at this the Galilean relativity. So now that we let's say we understand hopefully what inertial reference frames are, we understand that all the experiments that we do will agree on um, pretty much same time and same let's say same type of motion, right? So that means the predictions that can be made will be uh, absorbed. So then we're going to then look at in terms of what we call an event. Okay, so then event is some physical phenomenon that can be basically observed by different observers. One can be at rest, the other one can be moving, to the right, the other one can be maybe moving to the left. Doesn't matter. But one thing we have here is this is an event and it's a physical phenomenon and it has coordinates that can be, basically the spatial coordinates, x, y, z, and the time coordinate to represent the position and time. Okay. That means when something happens, you can only describe this event by not only pointing out where it happened, that means, some kind of position, and also when it happened. Okay. For example, your birth is an event. So when you were born, there was a very specific location when you were born, like let's say hospital, right? XYZ, but also a time. Because if you give me just the position of the hospital where you were born, well, probably there are children, uh, there, children basically burning that the hospital for every second, right? So I wouldn't know, let's say, which one is yours. Um, if you give me the time, I wouldn't know which hospital because different maybe at that time when you were born, there are like hundreds of other kids were born in like let's say just maybe in the same hospital, but you can imagine other places as well. That means, but if you give me the location and time, then I can pretty much point out that specific event. So that's kind of what we have. That means event has x, y, z, and t combined together. It means we have to give spatial coordinates x, y, z, to give us three-dimensional coordinates and the time. That means all of for everything for in this chapter will be in terms of this. So if there's an event, we also always have to include all of those measurements. All right, so let's start with this. For example, you have here's a coordinate system that I'm going to do. So we're going to call this x, y. We can just make it two-dimensional. So that means we can think of it x, y, z, but as a for the purpose of drawing, let me do that two-dimensional. So x and y. So we're gonna use this. So I'm gonna call this inertial reference frame S. Okay, so kind of like that. So this is the inertial reference frame S, and all the reference frames are going to be inertial. So even if let's say I don't mention this is an inertial reference frame, you need to understand that all the reference frames I'm going to be dealing with in this chapter are inertial reference frames. Okay, so let's say you are standing here. Okay, and let's say your friend is standing right next to you. So that's your friend right next to you. Right? It's hard to do like let's say on top of one another. So let's imagine that's that's your friend. Okay. Now what I can say here is then I'm gonna have this reference frame S represent you, and then I can represent then reference frame S prime, which will then represent your friend. So let's say here's your friend's reference frame is going to be like X prime and Y prime. Since you guys are right next to one another, then O and O prime, which means that all the coordinates are exactly the same for both of you. So basically, both of you are right next to one another. So the reference, the origin is exactly the same, horizontal position is exactly the same, and things like that. All right. So I'm doing this because, for example, if there is some kind of event, for example, some kind of firecracker or something like that. So let's say here's a firecracker, right? So there's a firecracker, and both of you see the firecracker. Then, because you guys are right next to one another, both of you then will measure the positions of this firecracker. So let's say, with respect to the origin, for example, right, your reference position to be X. So this will be your measurement, and then this will be your friend's measurement, X prime. Okay. And since what you have here is O is equals to O prime, that means your reference position origin is exactly the same, then you will also agree on the position of the let's say the firecracker, horizontal position. Well, you will also agree on a vertical position of the, let's say this will be Y and Y prime, right? So both of you will agree on that. And also the Z equals Z prime. That means primed are the measurement done by your friend, non-primed are the measurement done by you. And so it's some kind of if there's a this firecracker, right, then your measurement will be exactly same as your friend's measurements, and even T is equals to T prime. You will agree when it happened, because you are right next to one another, and you will see that let's say that event. That means all of those things will be the same. Now, one thing we have here is you both are at rest. Both of you are at rest next to one another. So there is no relative motion between you. So everything is exactly going to be the same, which is, something you would definitely expect. What we're going to do next, we're going to assume that, let's say your friend starts walking. So let's say your friend starts moving. So then what we're going to do here, we're going to look at it in terms of, all right, so this is you. Okay, this is you. That means I expect that this is your reference frame S, right? So with Y and X. But then let's say this is your friend that is now moving relative to you. So your friend is moving relative to you. Well, your friend is moving with the velocity V. So then, but I have S prime as a reference frame representing your friend. Okay, so that means I can say then your frame is in the reference frame S prime, which is again is an inertial reference frame, because your frame is moving at the constant velocity relative to you. Okay. So this V always represents velocity of the, so velocity of S prime reference frame. Okay. That's a velocity of the S prime reference frame relative to the S reference frame. That means how fast your friend is moving relative to you. Now, what I have here is then, this is, you can see, right? This is then this position of, you can say sort of like the origin, right? Between your origin and your friend's origin. Remember, before it was your origin and your friend's origin were exactly the same. But now your friend is moving with some velocity v. So then the origin, the distance between origins change. So let me call this d here representing that, right? So it means now what you have here is that O prime is equals to basically some this distance d, right? So let's say O and O prime are not the same. That means O prime is moving with that distance d, but that distance d is not constant, right? As the friend is moving, that changes. Okay, so you can say like sort of like, let's say O prime is equals to O plus d, but then this d here is variable, so I can just represent it as v times t. Remember, distance equals or think like this. So speed is equals to distance over t, because as you're moving with some speed, right, then you're going to change the distance. So then I can rearrange this where I can say d is equal to v times t. That means this v times t represents that changing time varying distance between you and your friend reference frame. That means in a way that's the same. So I can just get rid of that. So vt again represents the distance that is changing between you and your friend as the friend is moving away. Okay. Now the idea is that if that if now there's another event, so here's that event, right? P is event. Then both of you again start making measurements. One thing you have here is if you're measuring, then the position, horizontal position of that event will be this, right? So this will be that far away. So let me collect same thing here. So this will be then the position of that event measured by you in your reference frame S. Okay. But your friend is also measuring, and he will measure this. He or she will measure that as a reference, as the position of that event. Okay. Then X prime and X will no longer be the same because the S prime reference frame is moving relative to the S reference frame. So then you can see, right, the measurement, um, even though measurements are not the same, but in a way you can see, right, you guys more or less will agree exactly where the object is. So one thing we can do here is then we can develop an equation that's sort of like relates those two measurements. Okay, because one thing we can see that x being measurement uh, done by you in your reference frame, and x prime is the measurement done by your friend in his or her reference frame, and the difference between them is that x prime is equals to, or x is equal this x, right? Or x is equals to x prime plus this distance v times t. Okay. That means x is equals to x prime plus vt. So this is how your measurements will agree, just like origin, right? Origin also, remember, o o is equals to o prime plus vt. Okay, so o equals o prime plus vt. So then what we have here is this is called a transformation equation that allows you to relate those two measurements, your measurement with your friend's measurement. Okay, and what you have here is, let's make a simple an example with some numbers. Let's say your friend is moving at 10 meter per second. Let's say your friend is, let's say it's moving at 10 meter per second. And then what they do here is, let's say when the event happens, your friend measures this x prime, the position, to be let's say 3 meters from where he was. So that's the position of that event, 3 meters. Right. So then what I can say here is, if that event happened at t, both of you agree that the event happens at 3 seconds, let's say, right, after your friend, let's say, started moving relative to you. Let's say your friend started moving, and then 3 seconds later that event happened. So then your friend measured 3 meters, and then what you will measure basically will be 3 meters, your friend's measurement, plus velocity, which is how fast your friend is moving relative to you, which is 10 meters per second, times the time, 3 seconds. So for you, that measurement will be basically, 33 meters. That means position of that event is 33 meters relative to you. Because if your friend was moving at 10 meters per second for 3 seconds, that means he was already 30 meters away from you. And then if you measured an event to be 3 meters away from him, that means relative to you, it's 33 meters. Okay. So that's kind of what we can do. We can always assume that at t equals 0 is when it's right here, right? This is t equals 0. This is when your friend and you were right next to one another, the rest relative to one another. And then at t equals 0, he started moving. So then 3 seconds later, let's say there was an event. Okay. Your friend was already 30 meters away from you when that event happened. So it measured to be 3 meters. And then that means relative to you, that event is 33 meters. Okay. So these equations are basically representing what we call the Galilean transformation of coordinates. That means you have xyzt of the event relative to you in a reference frame S. X prime, y prime, z prime, t prime is the measurement relative to your friend in a inertial reference frame S prime. Then the relationship between the coordinates of you and your friend will be x is equals to x prime plus vt, y equals y prime, z equals z prime, and t equals t prime b. That means you will always agree on time. That's one of the things about Newtonian mechanics. Time is absolute. That means all the observer will agree on time. That's one of the things that we have from the Galilean Galilean relativity. You can also rearrange, right? So just mathematically, just rearrange and solve for the x prime. X prime then will be x minus vt. Y prime equals y. Z prime equals z. That means you can, if I, for example, if I go back over here, see if I had given you this first, I said, like, let's say you measured that to be 30 meters 3 seconds later after your friend was moving at 10 meters per second away from you, then you can say, all right, so x is equals to x prime plus vt, then rearrange, then x prime equals x minus vt, then x prime equals, so, sorry, the, what I meant, so this is, what I meant here is that this x is 33, let's say, you measure the position of the event is 33, then you can say it's 33 minus then 10 meter per second, 33 meters minus 10 meter per second times 3 seconds, then you will measure to be x prime as 3 meters. That means you can just rearrange and solve for the position that your friend will measure. Okay, so that's kind of what we have. All right, so now one of the things we can also talk about here is, let's say, if I go back here, now that we know all that, so imagine what I have here is this. Maybe there's not an event over there like that, let's say, but maybe there is, instead, your friend, let's say, I don't know, throws a ball. So let's say your friend throws a ball, and here's the ball, and this ball is moving with some what we call speed. Remember, v is used for the velocity of the s prime reference frame. So then velocity of any object, then we're going to give it letter u. So this will be u, which is the velocity of the ball. But let's say this is measured by your friend, u prime. So let's say your friend throws a ball, and let's say this is 20 meters per second. Okay. So I'm using u prime because that's a measurement done by your friend. So your friend throws this ball at 20 meters per second. Then what will you measure to be the velocity of the ball? Is it going to be 20 meters again? Well, let's find out. We can easily see this by looking at this equation. X is equals to x prime plus vt. Remember, you know that position of that, let's say position of the ball, for example, the instant it's moving at 20 meters per second, you can then use this equation to calculate, right? But one thing we have here is, if you talk about velocity, remember velocity is the rate at which the position is changing. That means what we do here is we take the derivative of this one. So dx dt equals then dx prime over dt prime. Remember, t equals t prime, so it doesn't really matter. Then plus dt of this vt. That means derivative of each term with respect to time. We're going to take dx dt to be then the rate at which the position of that ball will change relative to u. So that's going to be ux, x representing horizontal component of that. Dx prime dt prime is then ux prime, which is the velocity of the object relative to your friend in the s prime reference frame. Then plus, well, it's a derivative of vt, so then we'll just get v. Well, let's see then. Remember, your friend was moving at 10 meters per second away from you, and then he throws a ball that is moving 20 meters per second relative. While he was moving, he throws the ball at 20 meters per second. Then what you will measure is 20 meters per second that your friend measures plus 10 meters per second that your friend was already moving at that speed. Then what you will measure here is 30 meters per second. So that's what you will measure, 30 meter per second. If you're still confused about this, remember, if I go back to this over here, right, uh, to this experiment, remember, because the person in the truck is not moving this could be considered as your S prime frame. This is as your S prime frame. See, when you do an experiment in an S prime frame, what you have any experiment, if you throw the straight up, it means it's not going to have any type of horizontal component, right? It's just going to go straight up and down. But if you look in from, let's say, from the ground, right, as a stationary observer from the ground, what you see here is that the ball that goes straight up, but because the reference frame S prime moving with some kind of horizontal velocity, then you will see the ball also have a horizontal velocity. That means you will see that ball going projectile instead of just a straight up or down. So that's what we have. That means because if your friend was stationary and throws the ball at 20 meter per second, you will also measure it 20 meter per second. But because your friend throws as he or she was moving at 10 meter per second, that means the ball that the ball that let's say you will measure has to be take into account that 10 meter per second. Okay, because relative to you is going to be then 30 meter per second. All right, so and that's what we have over here. That means once we take the derivative of that, so then I can say ux equals ux prime plus v, uy equals uy prime, uz equals uz prime, or you can just rearrange and solve for the uh, u prime measurement, right? That means if I give you if I give you the measurement of the ball relative to you, then your friend can then do the measurement, right? So for example, if here's your reference frame and this is you, so if you throw the ball, then your friend in S prime, let's say reference frame, can measure that. For example, let's say your friend was moving at 10 meter per second, right, relative to you, and then you throw the ball at 5 meter per second. That means you throw the ball at 5 meter per second. Relative to you, that ball is moving to the right at 5 meter per second. Now the question is, what will your friend measure? Well, all you have to do is just plug it into this equation. Then this will be, a 5 meter per second minus the velocity at which your friend is moving away from you, and that's 10 meter per second. That means relative to you, ux prime is equal to then the negative 5 meter per second. Now the question is, does it make sense? Well, it should, because relative to your friend, when your friend is moving at 10 meter per second relative to you, one thing your friend can say is that, you know what, I'm not moving. My friend, which is you, is moving back at negative 10 meter per second relative to me. Because we can say that, right? We can say that instead of having S prime moving to the right at 10 meter per second and S moving at being at rest, then we can say that, you know what, S prime, reference frame is not moving, and S, reference frame is moving backward at negative 10 meter per second. That's one thing we can do. All right. So that's why negative 5 meter per second is that instead of you moving backward at negative 10 meter per second, because the ball is moving toward your friend at 5 meter per second, your friend will only see the ball moving back at only 5 meter per second rather than 10 meter per second. All right. So think about it. Hopefully it will make sense. All right. So these are known as a Galilean velocity transformation. So it leads to serious contradiction when applied to object moving at high speeds, which we'll see in a little bit. But these are the transformation equations that we can have every time the object is moving relatively like let's say everyday speeds. Okay, so here's an example. So you have two reference frame S and reference frame S prime. Okay, so you have ball 1 and ball 2 about to collide and have their velocities shown in reference frame S. So what is the velocity u prime 1 initial of ball 1 in frame S prime? That means, let's say here's your friend over there, and your friend is going to be then measuring the velocity of ball 1 relative to him or her in the reference frame S prime. Okay, so let's look at that. That means what we can say here is this: u1 initial, okay, is equals to 2 meters per second, then we can see that reference frame S prime is moving to the left at the speed of 4 meters per second. So I can, well, this is a vector. I can say that this is 2 meters per second I hat. Then V, which is always the velocity of the frame, is then negative 4 meters per second I hat. All right. Then what I can say here is, using that equation, ux is equals to ux prime plus vt, remember, right? So that's the equation. So then I can rearrange. I can say ux prime is equals to ux minus vt. Okay, so I can, oh, sorry, there is no vt over that, just v. Vt is when you have a coordinate position coordinate, like let's say calculation equation for the velocity doesn't have t. So then this is basically my equation. So this will be equals to ux, which is 2 meters per second I hat, then minus v, and well, v is negative 4 meter per second I hat. Then what I will get here for ux prime as 2 meter per second I hat plus this, that's going to cancel out, right? Become positive 4 meter per second I hat, because both of them I hat, I can add them together, 6 meter per second I hat. And that's basically the answer. That means the ball is moving to the right at 2 meter per second, but your friend is moving toward the ball at 4 meter per second. So relative to your friend, the ball will be moving at 6 meter per second, because it will be moving faster toward him because he's moving toward the ball. All right, so that's basically part A. Part B says, what is the velocity of u prime 2 initial of ball 2 in frame S prime? That means we pretty much do the same thing for ball 2. Let's write it down. So this is the measurement of the ball 2 initial relative to u. Let's remember. So let's say this is u. So this will be negative 4 meter per second I hat. Then I have the velocity of the ball, velocity of the frame S prime, which is negative 4 meter per second I hat. Then equation ux prime is equals to ux minus v. So negative 4 meter per second I hat minus negative 4 meter per second I hat. That's basically the v, right? Well, we'll end up with 4 meter per second I hat plus, negative 4 meter per second I hat plus 4 meter per second I hat. Then I'm going to get 0. Right? That means with respect to your friend, the ball 2 is actually not moving. Why? Because your friend is moving toward the ball. Imagine this, right? Imagine if uh, you throw a ball, but then you are able to, let's say, drive on your car as fast as the ball. So then what you will see is just the ball just sitting basically in air, but right next to you, not moving, just sort of like, seems like stationary, but it's not. Just both of you moving at the same speed. So the relative to you, then the ball is just at the rest, because both have the same speed in the same direction. Okay, that's what we have. All right, so now let's look at then Einstein's principle of relativity. So one of the things we have here is Einstein proposed a theory in which um, it resolves the contradiction between Galilean relativity and the fact that the speed of light is the same for all observers. So basically, we're going to see that why there was a need to let's say modify the Galilean relativity. Okay, so one of the things we have here is Albert Einstein obviously had already been exposed. It means, like, one of the advantages that he had was that he already knew of the fact that light is an electromagnetic wave, and Maxwell's equations show that light has a speed in vacuum as 3 times 10 to the 8 meter per second, and it was verified by the experiment already. So the Hertz did an experiment to demonstrate that the light indeed is an electromagnetic wave by discovering the radio waves. So one of the advantage of the Albert Einstein is that he knew about electricity, he knew about magnetism, he knew about the light being electromagnetic wave, thermodynamics, and everything that, well, Isaac Newton didn't know about much, right? So at least, in a way, we're talking about, like, let's say, advances in physics for over 200 years, almost 300 years, right? So then one of the things we did have here is this. So if I go back and very quickly remind you the principle of Galilean velocity, the relativity, it was that um, the laws of mechanics must be the same in all inertial frames of reference. So the laws of mechanics must be the same in all inertial reference frame. One thing Albert Einstein changed is this: all laws of physics are the same in all inertial reference frames instead of laws of mechanics, which means it's not just mechanics, but electricity and magnetism and optics and thermodynamics, right? They all must be the same in all of the inertial reference frames. And which means, like, let's say, not just mechanics, especially electrodynamics, right? Especially the fact that light is being electromagnetic wave should be the same for all inertial reference frames. Okay. Now, one thing we have from there is basically this. His other postulates is this: the constancy of speed of light, which means that the speed in all inertial frames, regardless of the velocity of the observer or the velocity of the source emitting the light, that means it's the same for all the observers. So again, speed of light in a vacuum has the same value in all inertial frames of reference, regardless. Again, regardless how they're moving relative to one another. Are they at rest? Are they moving away from each other, moving toward each other? What we have here, the speed of light should be constant for all the measurements. So these two postulates basically are the basis of special relativity. Okay. Now let's see, why do we need this, like, let's say, changes to the Galilean principle of relativity. Again, the important thing here is to understand that the constancy of speed of light means that we will always measure the speed of light to be c, which is 3 times 10 to 8 meters per second, regardless who's doing the measurement, where is the light, and how the reference frames are moving relative to one another. So let's look at sort of, like, let's say, measurement. So we have a reference frame S. Let's say let's say this is you in your reference frame S. And let's say here's your friend, S prime, with this is X, this is Y, then this is X prime, this is Y prime. Okay. Remember that reference frame S prime is moving with some velocity V. Now, one of the things we do here is this special theory of relativity, again, is specifically designed to understand the physics of very fast moving objects. It's much more general than Newtonian mechanics because it can describe, so like what happens at the low speeds and what happens at the high speeds. But obviously some of this effects is only visible, only noticeable when we're considering really high speed. So let's assume then, for example, this reference frame S prime is moving at 0.5 c, which is half the speed of light. Let's say it's moving at 0.5 c. And let's say here's your friend with some kind of flashlight. Some kind of flashlight. Well, a flashlight, then you basically have a light from the flashlight, let's say, going like this. And obviously the light from flashlight has a speed, and your friend will measure the speed. And let's say if your friend measures the speed of light in his reference frame, that means ux prime, which is the speed of light in the reference frame s prime measured by your friend, will be c. It's exactly the same. Let's say if you right now have a flashlight, turn on the flashlight and measure the speed of light coming out of the flashlight, will be c. So that means ux prime equals c. But then because your friend's, frame of reference is moving at 0.5 c, what you will measure the speed of light to be, according to the the Galilean equations, it will be ux equals ux prime plus v. Remember, right? Which means that what your friend measures, which is c, plus what your friend's frame of reference speed, which is 0.5 c, that means you will measure the speed of light to be 1.5 c. That means according to you, light is moving at 1.5 c, but that's already a violation of the Einstein's principle of relativity, because it says the speed of light in a vacuum has the same value in all inertial reference frames, regardless of the velocity of the observer or the velocity of the source emitting the light. Observer is in the frame S, source is in the frame S prime, and they're moving at different speed relative to one another. But if you are measuring the light, any observer should always measure that to be C. That means this cannot happen. You cannot measure the light to be at 1.5 C. Or for example, if this light actually moving in this direction, right? So let's say your frame measures negative C, which is just to the left. That means your measurement then will be, you know, sorry, let's say C minus zero point 0.5 C. So then you get zero point 0.5 C. That means you will measure the light moving toward you at half a speed. Again, that's cannot happen according to the Einstein's principle of relativity. So that means you can see that if we try to use Galilean principle of relativity, we're not getting the correct answer for the speed of light. We're getting higher than speed of light speed, higher than c, or lower than c. But this is not, basically cannot happen, right? This is not the measurement that is actually experimentally observed. That means if we look at experiments, experiments show us that regardless who's measuring, the speed of light is c. All right. So that's why you can say, right, this is a sweeping generalization of the principle of Newtonian relativity, which refers only to the laws of mechanics. Okay. So now that we are understanding that laws of all physics should be obeyed, including the speed, the speed of light, which is technically electromagnetic phenomenon, not mechanics. So we need then modification to this, the transformation equations. That means if we want to find how fast the speed of light is moving, we need to have an equation that basically gives us that. Okay, that means what we have here is there is no longer what we call an absolute motion, and there's no longer going to be an absolute time. Okay, because two observers should be measuring the speed of light to be c. And since if this is constant, that means the consequences of this is that the distance measurement between two observers at different reference frames should be in disagreement, and the time measurement should also be then in disagreement, because the simple c is equals to distance over time. That means in order for this c to always be constant, then d should be flexible and t should be flexible. That means they should not be constant, they should not be absolute, they should be then changing to accommodate for the speed of light to be constant always. That's why we're going to be looking at two different types of consequences of the special relativity, one dealing with time, the other one dealing with length, or the distance, basically. All right. So you can see now we're going to be looking at the consequences of relativity. So that starting with time measurements. So time measurement depends on the reference frame in which the measurement is made. Before it didn't. Remember, Galilean principle of relativity states that t equals t prime regardless. Okay, that is absolute time. But here, consequence of this is that if you're measuring the time of an event in reference frame S prime, the reference frame S will measure a different time for the event, or different, a measurement of the time interval for something. Okay, that means events, you can say, right, there's no longer an absolute time. So events at different locations that are observed, for example, to be simultaneous in one frame of reference, will no longer be simultaneous in a different frame of reference. Okay, that means this is concept called simultaneity, and simultaneity before was absolute. That means if something is simultaneous in one reference frame, would have been simultaneous in another reference frame. Okay, this is no longer true. Consequence of specialty of relativity is if you see two firecrackers at the same time, then you can conclude those firecrackers happened at the same time. But if somebody is moving relative to you and looks at those two firecrackers, he will never see those firecrackers, to be simultaneous. Because if I see them simultaneous, somebody else moving relative to me will never see that to be simultaneous. Okay, that means this specialty of relativity abandoned the assumption of simultaneity. Okay. So I would like to describe or show you this little clip, which kind of talks about that simultaneity, how in old classical relativity concept, you can assume that simultaneity is true for all the observers. But this little clip, it's again, it's kind of like old, but it very nicely demonstrates, this new, a simultaneity of relative to the specialty of relativity. Okay, so let's watch it.
Imagine two observers, one seated in the center of...
Try again.
Imagine two observers, one seated in the center of a speeding train car, and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees two bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time. So he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicted, the passenger does notice the flash from the front before the flash from the rear, but her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct? The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike? Einstein tells us that both are correct within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
All right, so that means two events that are simultaneous in one reference frame are in general not simultaneous in the second reference frame, moving relative to the first. Okay. All right, so simultaneity is not an absolute concept, but rather one that depends on the state of motion of the observer. Okay. All right, so again, that means both of those observers were correct. It just the reference frames were moving differently, so they cannot agree on simultaneity. All right, so here's one more example here. So if Anne and Bill are standing 1,200 meters apart. A firecracker, which is you can think like it's an event, right? Explodes 900 meters from Anne, and she sees the light flash at t equals 5 microsecond. So we're going to look at in terms of at what time did the explosion occur, and we can assume that speed of light has a speed as 300. Remember it's 300 million meter per second, or you can just say it's 300 meters per microsecond. That means during each microsecond, light travels 300 meters. Okay. So also our sees flash and firecracker explodes the same event, and if not, which is more significant? And at what time does Bill see the flash? All right, so let's look at this example. All right, since both Anne and Bill are at rest relative to one another, in a way, one thing we can do, we can assume that this is just one inertial reference frame, where what position of Anne is then the origin, the reference position. Now, think like this. Then what we have here is when the firecracker happened, right, basically explodes, it travels in all directions, right? So that means, let's say, when we talk about, with respect to Anne, then as soon as the firecracker explodes, it has to travel basically this distance to reach N. So let's say this is our, delta x. So then delta x is the distance from the event to the position of N. And we can see, right, that's basically 900 meters. Okay. And speed of light, because, we're given in terms of meters per microsecond, can be then written as 300 meters per microsecond. Now, we know that general equation for that relates speed, time, and distance is speed equals distance over time. Okay. Then we can rearrange and we can say then time is equals to distance over speed. So this is 900 meters divided by then 300 meters per microsecond. So we cancel out. We should then get 3 microseconds. That means the time it takes for the light to reach N is 3 microseconds. All right, so it says, at what time did that explosion occur? Well, we are given that N sees the flashlight at t equals 5 microsecond. Well, but it only takes 3 microseconds for the light to travel that distance of 900 meters. That means the time of the firecracker is the difference between when it sees and minus how long it has to travel. That means 5 microseconds minus 3 microseconds. So then we get 2 microseconds. That means that, the time for that means, the time for the firecracker to explode, right, when it exploded, is 2 microseconds. That means the time of the event, right? T is equals to 2 microseconds. That's the time of the event. Okay. And what we have here is it says, are seeing the flash and the firecracker exploding the same event? Well, obviously, it's not the same event, right? So firecracker exploded at t equals 2 microseconds, and saw the firecracker at t equals 5 microseconds, which means they, you have different, different time for those two events. So that means that they're not the same thing. Okay, seeing and actually happening are two different things. So what's more important here is the firecracker exploding, right? I mean, when the firecracker explodes, well, it doesn't matter if it's Anne is there or not. Firecracker exploding means it's going to explode. It's an event. So Anne being there is just basically she can see that. Someone else can see that. Maybe the third or fourth person can see that. But I mean, the firecracker explodes regardless if there was anybody there to see it. Next, it says, at what time does Bill see the flash? Well, we can see that in terms of the distance between event, where the firecracker exploded, and Bill here is only 300 meters, which means that it will take only 1 microsecond, right, for the light to travel this distance of 300, since it's 300 meter per microsecond. Again, we can do this, right? We can say this is delta x1, this is delta x2. So then TB for Bill, right, is equals to delta x2 over c. So then this 300 meters divided by 300 meter per microsecond. So then you get 1 microsecond. Okay, that means it will take only 1 microsecond for the light to travel to Bill. Now, one thing we already know is that the time of the event is 2 microseconds. That means when t was equal to 2 microseconds, the firecracker exploded. Then what time will the Bill see the flash? Well, 1 microsecond after that, which means that for Bill, right, he will see the explosion at exactly t equals 3 microseconds. That means this is pretty much the time of the event, okay? But t equals 3 microsecond is when Bill will see that. But again, in order for him to figure out when the explosion had occurred, he has to factor out, right? He has to take that the time of travel out of the equation, right, in order to get that exactly the time of the explosion, which is basically 1 microsecond after he sees that. That means he sees this, he sees the t equals 3 microsecond, 3 microsecond. That's when he sees the event. Where Anne saw that that event at 5 microseconds. All right, so those are basically just again, it's a simple example showing that sometimes you can write the speed of light as 300 meter per microsecond if you're okay with writing time in terms of microseconds, and also in terms of seeing an event and event happening are two different things. All right, so now here we have Anne and Bill are still standing 1200 meter apart. A firecracker explode 300 meter on either side of Bill. That means there's a 900 meter and 1500 meter from Anne. Okay. Anne sees the two flashes at the same time. According to Anne, were the explosions simultaneous? Okay. So, which means now what we're dealing with is, if we go back here in this diagram, okay, clean it up. Imagine now there are two explosions. Okay. So one is there, the other one right here. So 900 and 1500. Okay. So one thing we have here is, let's say, let me kind of remove this. So we know that those those two positions, right, 900 and 1500, is exactly same, 300 meters from Bill. Okay. But what we're told here in the example here, in the next example, right, is that um, according to Anne, so were the explosions simultaneous? Okay. But what happens is that we know that she sees the two flashes exactly at the same time. Okay. So she sees it exactly at the same time, which means um, if she sees it at the same time, does it mean it's simultaneous? Well, let's see what we have. In terms of then, for her to see them at the same time, remember, light has to travel. So this light travels this distance of 900 meters. The other one then travels distance of 1500 meters. Okay. So think like this. That means, let's call this event 1 and this is event 2. The light from event 1 has to travel 900 meters. Light from event 2 has to travel 1500 meters. Okay. So think like this. If they happened exactly the same time, would she see them exactly the same time? Okay. Remember, seeing and happening, right, for the event explosion, right? There are two different things. But still, if she sees them exactly at the same time, you have to understand that you have to take into account the fact that event light from event 2 has to travel extra distance, right? Extra distance to get to N. Okay. So for N to see two explosions at the same time, the one that is further away, right, 1500, must occur earlier, because it has to travel this distance first, and then when the second, this first one happened, right, then travel exactly same time as this one over there, so that she sees them both exactly at the same time. Okay. That means we have to understand that this is that extra time that needed for the event 2 to reach event 1, and when it reaches event 1, then event 1 happens, then they both basically, you know again, I'm just calling this event 1, event 2, but doesn't mean that event 2 happened after event 1, so you have to understand that. So maybe it was a poor choice, but the idea here is you have to, in order for the event 1 and event 2 light reach N exactly the same time, event 2, right, firecracker at 1500 meters, had to happen earlier. Okay, and it had to travel one 300-meter distance plus another 300-meter distance in order to get to the firecracker 1. Then they travel together exactly same time, which means we know that every 300 meters light covers in 1 microsecond. That means it had to happen 2 microseconds before, so that takes 2 microseconds for it to reach event 1, firecracker 1, and then they both travel together. Okay. That means what we have here is they did not happen exactly same time. Okay. So firecracker 2 here happened 2 seconds earlier. Now for the other guy, for Bill, what we have is it has exactly same distance between both each firecrackers. Okay. That means one thing we have here is that Anne and Bill, they are not moving relative to one another. Okay. That means this is you know they should agree on simultaneity of the um, let's say of the events. If they were moving relative to one another, then let's say that was different. But here they're not moving relative to one another. Now Anne agreed that basically the firecrackers didn't happen exactly at the same time because they had to travel different distances. So if she sees them exactly at the same time, they would be simultaneous only if they were exactly same distance from her, but they were not, so they're not simultaneous. For Bill, they are exactly same distance from him, but we already agreed that they're not simultaneous, and Bill is at rest relative to Anne, so he has to also agree that it's not simultaneous. That means what happens here is he sees, because the firecracker 2 happened 2 microseconds earlier, he will see that 2 microseconds before he sees the other one. Okay. That means he will conclude that they are also not simultaneous because they're all both of them the same distance from him. So he will say that he will see the 1500-meter one first and then 900-meter one. All right. So let's look at then next in terms of the consequences of special relativity. So for this one, we're going to be then looking at in terms of how the light, in order to make sure that the speed of light is constant for all the observers, we have to understand then there is no absolute motion, no absolute time. Okay. To do that, we have a simple experiment. So let's say you have a reference frame S prime, okay, that is moving with some velocity v. You can see, right? We're moving with some velocity v, and we have an observer in the reference frame S prime, and she does an experiment. An experiment is pretty straightforward. So you have a light, um, basically a flashlight, will go up, hit the mirror, and come back down. And let's say there's a sensor over there that detects the light. Okay, that means the distance d between the sensor and let's say the mirror is lowercase d. So the total distance will be the light going up, hitting the mirror, coming back down. Okay. That means what we have here is that the flashlight, right? Flashlight emits a pulse of light directed at the mirror. That's event one. And then the pulse arrives back at the, after being reflected and let's say registered by the sensor. And that's, let's say, then event two. Okay. So it's relatively straightforward. And if you talking about this person, let me do like P prime, right? Person prime, right? That's basically because she is in the prime reference frame. Okay. She's in the reference frame S prime. And she's where the experiment is done. So what she will measure here is distance, to be going back and forth is 2d. And then since the light is moving at the speed of light c, then the time of the event 1 and 2 together will be 2d divided by c, which is, remember, so it's a distance divided by time. That's for speed. So then rearrange distance over speed is a time. That means this will be the time measured in reference frame S prime by actually, let me be like O prime, which is observer prime. Let's call it observer prime. So observer O prime measures delta t, and we're gonna call this P for the proper. P is gonna, you're gonna see, it's gonna be for the proper time. Okay. So now it's a proper time because it's being measured by the person who's in the same reference frame as the experiment itself. Okay. That means O prime is measuring proper time because she's in the same reference frame where the experiment is done. So that means 2d divided by c will give us the time. All right. Next, what we're going to do here is we're going to look at then what happens if the same experiment is observed by someone else. Okay. By someone else is, let's say, someone who's not in the moving reference frame. So here's that, let's say, reference frame S with y and x. And let's say this person here is x prime, y prime, and this is s prime, reference frame. And reference frame s prime is moving with velocity v. All right, so then what he will observe, right, observer O, will be, because the experiment, because the experiment done in a moving reference frame, the light, instead of going straight up and straight down, remember that very first experiment that we looked at, when object is, in a moving track, if you throw an object upward, it's going to go straight up and straight down in the moving reference frame, but the observer will see a projectile. Same thing happens here. For the stationary observer in a reference frame S, the experiment will be basically the light goes like this instead of straight, right? It will basically move like that, hit the mirror, and then come back down like that. Okay. That means you have completely different, geometry of the trajectory, right, for the light. Okay. Now let's remember that delta t prime was just the distance, which happened to be, let's say, 2d divided by speed, which is c. Now, one thing they both will agree is that the light is moving at the speed of c. That one thing they agree, but nothing else they agree on. The distance, the time, those two things then has to be modified. They cannot be the same anymore, right? Otherwise, the c will not be the same. So that means one thing we end up with is this. For the distance, this is the distance that traveled by light. Okay. That means we need to find how long it took for the light to travel that distance. Okay. While the reference frame S prime, right, the train was moving to the right. Well, if we do that, then geometry tells us that this length is basically c times delta t over 2. That means this one is also c times delta t over 2. And then this side of the triangle then is v times delta t over 2. Okay, basically break it down into just two parts, right? One going up, one coming down. So we have basically it's using the triangle because this has to be the distance t, right? This is just straight up distance from where the sensor is or the flashlight is and where the mirror is. That means then what we have here is you can then relate this using the Pythagorean theorem, where then equation tells you that c times delta t over 2 squared plus, or it equals to, which is the hypotenuse, right? So then this is equals to v times delta t over 2 square plus d square. That means if I look at this, right, that's how those are related. Okay. Well, if we rearrange this, basically we just plug it out and do the calculation. One thing we will see for delta t, the time interval, this will be then 2d divided by square root of c squared minus v squared. Okay. So then what we'll do is that we'll take the c squared and factor out. So because I can write this 2d divided by c, c squared, 1 minus v squared over c squared. So I can just basically factor out c. Then I can remove that from the square root. So it becomes 2d over c, then square root of 1 minus v squared over c squared. Now, from here, though, we can see that if I kind of separate this, this is just 2d over c. Well, 2d over c is same as that delta tp, which was 2d over c. That means that part of that equation can be basically represented with the proper time. That means delta t then is equals to 2d over c represented as the delta tp, but then you have then the factor of 1 minus v squared over c squared. And you can see that what you have here is there's a disagreement in terms of the time. That means what you have here is 1 over square root of 1 minus v squared over c squared times delta tp, where this, 1 over square root of 1 minus v squared over c squared is basically the coefficient of the in front of delta tp. That means that's basically that factor that gives you a different time for the observers. That means you can see, right, one of the things you have here is when v0, let's say when the train, when this reference frame s prime was not moving, let's say when v is equals to 0, in this equation, if I plug in this for 0, then this term is 0. So then you have 1 over 1, then delta tp equals a delta t, which makes sense, right? If you have a reference frame s prime, right, the train is not moving, then if you do an experiment straight up or down, observer will also see straight up or down because there's no motion relative to one another. But if the train is moving, right, if the experiment is done in a moving reference frame, then any not moving reference frame will then see a different time interval. Okay. So this factor 1 over square root of 1 minus v squared over c squared, this is basically can be defined as gamma. Okay. Where gamma is pretty much this relativistic factor that we have. Then I can say then delta t, measurement done by the observer O of this event 1 and 2 combined, will be equal to then gamma times delta tp times the proper time. And one of the things you can see here is, for example, if I have the velocity, remember, so it's much more useful when you have a relativistic speed. So let's say this v here is equals to 0.6 c. Let's say that the train, right, where the experiment was done was moving at 0.6 c. If I plug in then for gamma, what I can see here is this is equals to 1 over square root of 1 minus 0.6 c squared divided by c squared. So then the c is going to c from top and bottom going to cancel out. So you just basically have 1 over square root of 1 minus 0.6 c squared, 0.6 squared. So this will give us 1.25. It has no unit. Basically, the gamma is a unitless quantity, but we get 1.25. That means this is equals to 1.25 times delta Tp. That means whatever measurement for time that we have for the observer O prime, that means, the, let's say, whatever measurement was done by this person here, right? Observer O prime, then observer O can measure 1.25 times that time. That means, for example, let's say proper time was, I don't know, 10 seconds. Then this will be 1.25 times 10 seconds, or 12.5 seconds. That means there's already a disagreement on time measurements. Okay. So this is known as time dilation. Okay. And if there's a object moving, basically relative to some observer, they will never agree on time measurements. Okay, so you can see, right? So you have two delta t's. Delta t, this is basically by some kind of observer that measures an event in a different reference frame. Delta tp is the time of the event in the same reference frame when it's done, when the experiment is conducted. That's why it's called a proper time. Okay, it's called the proper time, and it's always going to be the experimental measurement of the event in the same reference frame when, where the event is occurring. And that's why then measurement of that event from any other reference frames will be in disagreement with that, and it will always be more. That means measurement done by other reference frames will always be greater than the measurement done in the reference frame of the experiment. So this is known as a time dilation. Okay, so time dilation basically is a consequence of special theory of relativity. That means if you have an experiment where let's say, for example, so here's Earth and here's a person on Earth. So we're going to call this observer O. And then here's a spaceship, and I don't know, my spaceship looks like an airplane, I guess. So let's say this spaceship is moving at the speed of 0.9 c, 0.9 c, let's say. What I'm going to do here is I'm going to look at in terms of observer O prime measuring basically the 1 second interval on his watch. Okay, so delta TP, because this is the astronaut measuring the 1 second time interval on his watch, 1 second is then the proper time. Okay, that means basically for him, when the time passes, 1 second passes, right? For him is 1 second. That means, let's say, one of those analog clocks, right? The second, call it like a hand, and so it's a second hand, right? So hand that represents seconds. Um, so let's say it's 1 second for the astronaut. Then what will be for exactly same thing measured by an observer on Earth? Well, we use this equation. So we first find gamma, square root of 1 minus, so 1 over, so 1 over square root of 1 minus, then speed at which the reference frame S prime is moving, so 0.9 c over c squared. You can see that c cancels out. So then the gamma is equals to 1 over 1 minus 0.9 square. And if I make this calculation, I get roughly 2.3 seconds, or 2.3, sorry. And then delta t is equals to gamma times delta t proper, which is 2.3 times 1 second interval, so 2.3 seconds. That means it will take 2.3 seconds for that second arm to move 1 second. Okay, that means go one time, move one time, which means every time it moves it's 1 second. Now, which means there's a disagreement in terms of that. Now, what it means here is sometimes very confusing, right? So what do you mean, like, let's say 2.3 seconds? Well, think like this. So the measurement done by the astronaut of the second hand, right, on his clock, on his watch, is basically going to be exactly the same regardless of where he's doing this experiment. That means, if he was on Earth in his house, look at the uh, how long it will take for this for that arm to for the hand to move 1 second. It's exactly same for him. It's just 1 second, but because he is moving relative to some observer, this observer will see the same event, which is the second hand moving 1 second. He will see that happening at the lower rate. Instead of 1 second, it takes 2.3 seconds for that to happen. Okay. So that's what we have, a time dilation. So that's why, for example, if the astronaut goes to another star system and comes back, and for him it's, let's say, 14 years, 15 years, but this is 1514 with respect to his reference frame. And his reference frame, the time, right, will be different measured by the observer on Earth. Because as we agreed, right, the time seems to be moving slower for the observer O. That means 14 years, depending on how fast it's going here, right, will be completely different. Okay. We can even calculate, right? We can even calculate that in terms of what will be the time, right? So again, that will be based on the speed, which is, let's say, point nine c gives you a factor of 2.3. So if it's 14 years, then for someone on Earth it will be 2.3 times 14 years. All right. So roughly, let's say 30 years, right? So instead of 14 years on Earth, it will be 30 years. And it actually physically will be 30 years on Earth. That means for the astronaut, it takes 14 years to go and come back. But for someone on Earth, it took an astronaut 30 years to go and come back. Okay. Because astronauts was moving faster relative to the observer on Earth, the time of that event, which is going to another star planet and coming back, will be in disagreement. That's why, that's how this, let's say, we developed this, right? So measurement of the light going to hitting the mirror, coming back, was a disagreement for the two observers. Same thing will happen there. How long it will take for the astronaut to go and come back will be different for the two different observers, astronaut and, let's say, and the person on Earth. Okay, so that's kind of what we have. So the time dilation is not observed in our everyday lives. Okay, so at slow speeds, right? This gamma is so small that no time dilation occurs. But they still did some experiments where they they took two atomic clocks. They made sure that they show exactly same time. Atomic clocks is the most accurate clocks that we have. And they took another one, put it in the fastest airplane that we have, and this airplane went around Earth, let's say, as fast as it can several times, and then came back. So that means one clock stayed in the laboratory, the other one was in the airplane moving around very fast around Earth. But then when they brought and they compared, the times disagreed. That means the one that was, let's say, on airplane was running slower, because for if you're moving fast, your time is different relative to another clock that was not moving relative to you. Again, if you're an astronaut, for you time is not going faster. It's exactly same as you would be, let's say, if you were not moving at all. But relative to someone else who's not, or who's moving slower relative to you, for them, your your time is basically moving slower, because for them, let's say if you go 14 years and come back, for them that was 30 years rather than 14 years. Anyways, delta TP is called the proper time interval, and the proper time interval is a time interval between events as measured by an observer who sees the events occur at the same point in space. Okay, that means basically the same reference frame where the experiment is. And one of the difficulties about this type of problems is to identify who is the observer that measures the proper time. So that's why I try to always understand what's happening, where is the event, which is the reference frame, which information is given, so then you can make a correct calculation. All right, so again, so this is such a concept that is very difficult, intuitive. Like it's a very abstract idea. That's why, like, you will see like different ways of explaining this. So if a clock is moving with respect to you, the time interval between the ticks of the moving clock is observed to be longer than the time interval between ticks of an individual clock in your reference frame. Okay. So all physical processes are measured to slow down when these processes occur in the frame moving with respect to the observer. Okay. With anybody moving faster, relative to you, for them the time will be seems like it's moving slower, but only slow relative to you. For them, everything is fine. And this process is not science fiction, right? It's actually science fact. This process can be chemical and biological as well. That means they age slower than you. Anybody that is moving faster than you, they age slower than you. Right? That's why we have this sort of like, let's say, different paradoxes, right? So twin paradox, something like that, which we'll see. But this is something that has experimentally been verified. So for example, one of the experimental verification is um, we have what we call subatomic, exotic subatomic particles called muons. Okay, so there's the muons are unstable particles that have the same charge as an electron, but a mass 207 times more than the electron. So we always study about um, electrons and protons and muons, but there are actually other particles that are sort of like they have their own family. So our family of the particles is the one that we are composed of, are electron, protons, and neutrons, or quarks, if you want to go deeper than that. But there are also other ones. So let's say there's another particle, charged particle, that is just negative, just like the electron, but it is much heavier than that. So we call them muons. Now, these muons are unstable, means that they don't have a long life. So when they sometimes they can generate it, and then they can um, decay into smaller particles. Let's say become electrons and so on and so forth. So you can say, right, they are produced high in the atmosphere. Okay. Now, one of the things we have here is that, so here's an experiment. So there are two things. There's this basically the prediction, and there's an experimental result. Okay, so according to, let's say, prediction, what we have is this. So this is when muon created. Okay, so this is not this is using the classical let's say prediction. If I take the classical prediction, muons basically have a half-life of 2.2 microseconds, for example, right? So then delta t proper is equals to 2.2 microseconds. When we measure this reference in the reference frame at the rest with respect to them, that means you have someone right here measures this, and this is 2.2 microseconds. Okay, now they can, then what we have here is, because this is the proper time, this is their half-life, according to the how long it will take them to move down before decaying, if they let's say moving at some speed, which is approximately speed of light c, then non-relativistic or classical prediction would be they can only move about 6.6 times 10 to the 2 meters, which is roughly 600 meters, right, before decaying. Okay, that means they're at the higher altitude in the atmosphere, going down about 600 meters, they should decay and just be gone, right? So like, let's say, into smaller particles, lighter particles. So according to the classical theory, if you put a detector right here, you will not be detecting any muons because they will be long gone. Okay. Well, that's not what happens. What happens here is that this detector that you have actually detects a lot of muons. That means, let's say that detector is roughly, let's say, 5,000 meters below where they created. But according to the classical theory, about 600 meters, 700 meters, below the point of creation, they should be decaying. But they don't. They actually go down all the way to the detector, and we can detect most of them. So how can that happen? Like, how can they, have this life, let's say half-life, and we can then calculate how long they can move with that, let's say moving at the speed, how can then basically reach all the way to the to the surface of Earth. That was basically a mystery, right? So you can't really use the classical physics to try to describe that. Well, what we have here is then we have to understand, right? Then there has to be, like, let's say, this relativistic consideration. So the muon's lifetime is, well, is measured relative to the observer on Earth. Okay. So then what we have here is, if you then talk about from the muon, let's say, reference frame, you get then different values. Since delta t is equals to gamma down 10 times delta p, so that means, what we have here is, well, delta t then um, will be different, right? So that means what we're doing, we were thinking about, the time, this 2.2 microseconds, which is basically the time relative to the muon. That means, if when the muon created and muon destroyed is 2.2 microseconds. But you can only do that if you were in the reference frame of the muon. But we're not. We're in the reference frame of Earth. And with respect to reference from Earth, we should be then taking not the same time as the, from the reference frame of the muon, but time for the reference frame of Earth. That means we should then say that this is gamma times delta p. Okay, so gamma times delta p then gives us different, much greater time. So if you then get a much greater time, that means then the particle has more time to travel longer distances. Okay, that means 2.2 microseconds, 2.2 microsecond is the time measured if you were, like, let's say, moving with the muon. But obviously we're not moving with the muon. We're stationary on Earth. So relative to us, muon is moving, and if you plug in this and use the, let's say, whatever, I don't know, let's say muon is moving, maybe let's say 0.99 c or something like that, right? So then if you plug in this, then you get time that is much higher than the proper time of the muon, which means now they have a lot more time to go down, and that's what happens. Okay, because one of the things we have to also understand is that there's another relativistic consequence. Is for us, this distance is about 5,000 meters, but for a muon that is moving fast, that distance actually shrinks. So in their 2.2 microsecond, they go, they seem to be moving shorter distance, but not because it is a short, this is just because they are moving fast. For them, the distance shrinks. We're going to talk about that. It's known as a length contraction. Okay, so that's another consequence of relativity. Okay, so the last thing we have here is sort of like that astronaut that I was talking about. So it's another consequence of relativity, where if you talk about two twins, I mean, basically, a set of twins, right? So two, uh, one is speedo, one is go slow. So we have a speedo that travels to planet X 20 light years from the Earth, and light years is a distance. The distance it takes for the light to travel in 1 year. Okay, so that means you can technically, measure that distance in meters if you want to. So let's say then the speedo basically is in a ship that travels at the 0.95 c. So for him, he goes 20 light years. Now, after reaching planet X, he immediately returns to Earth at the same speed. When speedo returns, he has aged 13 years, but Goslow aged 40. Goslow aged 42 years. And if you notice that, interesting thing about those names, right? So he aged 42 years. Again, why? Because of the relativistic effect, right? So because Speedo was moving at the high speed relative to Goslow, he was experiencing much slower, right, rate of aging, right? So there, he only aged 13 years because relative to Goslow, his time was moving slower. Okay, so that means it took 42 years for him to, you know, basically go 13 years. in terms of the time disagreement. Okay, so this is again another consequence of um, relativity. That means if you're moving fast, for you time is moving, seems to be moving slower relative to a slower moving observers. Okay, because we take, let's say, Earth to be not moving at all, like let's say the ghost law is not moving at all, then you get sort of like the maximum effect. Okay, so they're twins, same age, but then they come back. One is age 13 years, the other one, or 14 years, the other one is 42 years. Okay, so that's another consequence of that. All right.